Hello and welcome to the Callum Cymru revision session for AS Further Maths. This is revision session 4 and today we're going to take a look at Hooke's law. Now, taking a look at the specification and teaching guidance from the WJC, most of Hooke's law is just contained in this top paragraph here. And in physics, you kind of look at this equation. We just take it a little bit further in further maths. You are not given the formula for Hooke's law in the formula booklet, so it is one that you need to learn. There's also a little bit about Hooke's law just a little bit further down here, where we also need to apply it to situations using elastic energy. Now let's take a look at what Hooke's law is. So we've got Robert Hooke on the screen here, and on the left hand side we've got a graph kind of demonstrating Hooke's law. You can see it here. So Hooke's law, he found that the tension or the thrust or the force was proportional to the extension or the compression of the spring or the piece of elastic that he was dealing with. In physics, I think you take the formula just to this level. In further maths, we sort of explore this constant a little bit more, and I guess the constant is made up of lambda over L. Where's my pen? There we go. The modulus of elasticity has got a unit of newtons, and we times that by the extension, divided by the unstretched length, and that gives us either the tension or the thrust, depending on whether we have an extension or a compression. Now, I think if you go and study this a little bit more, actually they take this a little bit further, and the modulus of elasticity is multiplied by the cross-sectional area of whatever you're dealing with. So we take it to a certain level in further maths. I suppose if you go and do a degree, you'll probably go a little bit further. Now, for our situations, Hooke's law is only applicable up to the elastic limit. So up here you can sort of see, you can imagine if you stretch a spring to a certain point, it breaks, or it doesn't become spring anymore, or the elastic nature of it changes. So we only have to deal with it up to the elastic limit. Let's take a look at a fairly straightforward question involving Hooke's law. I've put the formula in the top right-hand corner of the slides up here. You do have to learn it though. You are not going to get given that. So the questions can be quite wordy. An elastic string, natural length, and it tells you the weight. For all of these questions, I would highly recommend you draw a little sketch or diagram of what's going on, even if the question appears quite straightforward. So I've drawn a little sketch here. Now this question, this is an exam question. It's really easy though. I'd be very surprised if they gave you one that was this easy. But drawing a little sketch can just help, because here we've kind of worked out that our natural length, L, is 0.3, and the extension, X, is 0.25. The total length of the string, that's helped me work out the extension. There's a couple of things that I would usually add on to a diagram like this. I might add on the weight. So the weight here is 12 newtons, and then equal and opposite to that, you might have some kind of tension. Usually we will be looking at doing two things. We'll be applying Hooke's law, and we might also be resolving the forces. So I'll start by resolving my forces, and I'll take upwards as the positive direction here. So pulling us up, we have the tension, and pulling us down, we have 12 newtons, and that should equal 0. Because the thing is not accelerating, it's in equilibrium. That means that tension is 12. You probably didn't need to write that. You could probably just see that T was equal to 12. Then we go about and we apply Hooke's law. So Hooke's law says that T equals lambda times 0.25 over L, the natural length, which is 0.3. Then we have two equations. We've got one here and we've got one here. And we're going to substitute one into the other. So 0.25 lambda divided by 0.3 equals 12. That gives us lambda equals 14.4. Now the units for lambda is newtons. That is a very, very straightforward question involving Hooke's law and equilibrium. It's unlikely you'll get a question that straightforward, so we just need to look at a slightly more difficult example, and that's what I wanted to look at next. Now, if you're re-watching this video, you might like to pause the video and just try to sketch the situation that's given, and then have a go at the question yourself. So we've got two identical elastic springs. The natural length is the same as for each. That is the letter L. It's not the capital letter I. And lambda is 2 mg. The springs are joined at point Q, and the ends P and R are attached to fixed points. Let's just draw that into a sketch. There we go. So we've got P to Q and Q to R. P and R are attached, if you like, one is at the ceiling and one is at the floor. The total length is 4L. There we go. So the distance between P and R is 4L. And if we have a think about it, the natural length of each of these is L. Well, 4L, that's 4 times bigger than the natural length. So they must be being stretched a decent amount, I would imagine. And maybe I need to show that on this diagram as well. So the other thing that I'm going to put on the diagram is kind of splitting up the different lengths that I've got. Now, in red here, you can see I've got the kind of length of P to Q, and then in green, I've got the length of Q to R. And L is the natural length. So the natural length for both of them is the same. I'm kind of imagining that X is going to be longer because the particle Q has an element of weight that's pulling it down. So I think the stretch will be a little bit longer there. And I'm imagining that Y, which is the stretch coming from the other end, is going to be a little bit less. There is a potential, I guess, that Y might be negative because these things are springs. So it might be that instead of both of them being stretched, it might be that the bottom one is being compressed and that the top one is being stretched. I guess I'm not really sure. Maybe when I do some calculations, if I get Y as a negative, then maybe I might be getting a compression. Let's go ahead and do a little bit of work on this. The other thing I'm just going to put next to the diagram is my lambda is 2 mg. Now, to start with, I'm just going to look at my total length. The total length of this situation, well, it's 4L. Oops. 4L. And that is equal to one of the L's plus an X plus a Y plus the other L. I'm just going to kind of park that there because I think I might need that later. The other thing I'm going to do is I'm going to resolve my forces, and I need to choose the direction. I'm going to choose upwards as the positive direction. Now, I haven't drawn any forces on here, so that's what I'm going to do next. If I think going down, we've got the element of weight. Now, the particle has a mass of m, so my weight is mg. I've also got some kind of tension coming from the spring at the bottom. I'm going to call that T1. And I've got a tension coming from the spring at the top, and I'm going to call that T2. So if I resolve this now, I've got T2 acting upwards. Then downwards, I've got T1, so that must be negative, and also downwards, I've got mg, so that must be negative. because it's in equilibrium, this must equal 0. So that's kind of another, if you like, batch of marks that I might be able to achieve. Next, I'm going to think about Hooke's law. Now I'm going to apply Hooke's law to both of the springs. So we'll apply it to the top spring. T2 equals, so it's lambda. Lambda is 2mg times the extension I don't know, so I've called it x, divided by the natural length, and the natural length is L. Let's apply Hooke's law to the other spring. So we're looking at T1 here, and that's going to equal 2mg times y, because the extension for the bottom one is y, divided by the natural length of L. The natural length of both of them is the same. Now I'm having a look at these, and I feel like I want to kind of combine a lot of these together. So here it looks like I could maybe use this in my formula here, T2, and T1 I could use it in the equation here. The thing that I kind of would like to get rid of is either one of the x's or one of the y's, and here I can see I've got a y. What I'm going to do is I'm just going to rearrange this. So let's do this next to this. Up here, if we tidy this up, we get y equals 2L minus x. That would allow me then to substitute that y value in there. So let's go ahead and substitute these values into the equation for my forces. So instead of writing T2, I'm going to write 2mgx over L. And instead of writing T1, I'm going to write minus 2mg, and instead of y, I'm writing 2L minus x, all divided by L, take away mg equals 0. Just spotted I've missed off an m in there. Now it looks like I've got mg in every term here, so I'm going to cancel through the mg in each of these. Maybe I'll just write a 1 there, because there is still a 1 that I want to keep there. And then I could just bring everything together here. So here I seem to have a denominator of L. Maybe I should actually, here I could change this to L over L. So it's also got a denominator of L. And then I can write it with a common denominator. So we've got 2x minus, and then I'm going to do 2 times 2L. So that's minus 4L. And then 2 times x, but it's minus times minus, so it's plus 2x. And then minus at the end, minus L, all divided by the common denominator, which is now L, equals 0. If we think about this, we only need to think about the numerator here, equal to 0. So what have we got? 2x plus 2x is 4x, minus 5L, and that will equal 0. So that gives us 4x equals 5L. So x is equal to 5 over 4L. I think I'm nearly there. It says find the distance of the particle below P. So at the moment, I found that x is 5 over 4L. And I've got this L here, so I think I need to find the total distance kind of combined. So P to Q is equal to L plus X. Well, that's L plus 5 over 4L. So that's a total of 9 over 4L. So that's just a slightly harder question involving Hooke's law and a situation in equilibrium. Now, the two previous ones were a situation in equilibrium. This one is a dynamic situation. So we have got some acceleration involved. Again, it's a question with a lot of words, and we need to turn all these words into a diagram. So here we've got an elastic spring, and it's attached at one end to a particle, the other end's attached to a fixed point. It's on a rough plane, and the plane is inclined at an angle. This diagram represents the situation. It also tells us that there is some friction involved. Now, they often give the angle as a trigonometric ratio. So I'm just going to have a think about that to start with. So we've got tan alpha equals 3/4. That means that we've got here, this is alpha. So the opposite is 3 and the adjacent is 4. And this one must be 5 because it's a Pythagorean triple. So that gives us sine alpha, which is the opposite over the hypotenuse, so 3/5, and cos alpha, which is the adjacent over the hypotenuse, so that's 4/5. We do not want to go ahead and work out what alpha is, then you're going to make things a little bit more complicated. We've got lots of other important information in the question. I can just leave it there, that's no problem. I kind of like to see it very clearly, so I'm just going to make a note down here of some of the key bits of information. So lambda, I can see there's a mu value given, the coefficient of friction 0.2. I can see there's a natural length given, L, that's 1.5. And I can also see there is a mass, the mass is 0.5. You don't have to do that, but just like to see the information clearly. The other thing that we probably want to do is add some forces onto here. So I guess this spring, at the moment, it says the natural length is 1.5, and it says currently it's compressed at 1 meter. So that means it is wanting to push in this direction when it's released. So we will have some kind of thrust force acting in that direction. That means that opposite to that, we're going to have some kind of frictional force. We also get a normal reaction force going up, and then we have the weight 0.5, that's the mass of the particle, times gravity. I like to put on just an extra triangle here to split the component of the weight up. If this is alpha in here, then this is 0.5 g, and it's adjacent to alpha, so that means it must be cos alpha. And this is 0.5 g, and it's opposite alpha, so it must be sine alpha. And just having all those forces on a diagram, I find helps me decide where I'm going. For this one, it's talking about find the acceleration. So I think I'm going to need to resolve some forces, but I'm a bit nervous because I do have friction involved. So I probably need to resolve forces in 2 different directions. I'm going to resolve, to start with, perpendicular to the plane. So I basically say, what is that pulling us up kind of in that direction? I can see over here I've got R, so it's R, and then I think, is there anything else pulling me up? No. Is there anything pulling me down? Yes, it looks like this 0.5 g cos alpha is, so it's minus 0.5 g cos alpha. This is in equilibrium in the perpendicular to the plane because it's not floating up off the plane, so it can equal 0. That means that R is 0.5 g cos alpha, and cos alpha is 4/5, so this gives us 0.4 g because we're using the information from up here. So that's kind of resolved our forces perpendicular to the plane. That then allows us to find our friction. Friction is mu times R. So friction is 0.2 times 0.4 g. And that equals 0.08 g. Now, there's a few other things we want to think about. We want to think about resolving forces parallel to the plane, and we want to think about Hooke's law. It doesn't really matter what order you do it in, because eventually you'll find that you might get stuck in one bit and you just need to find the other part of your problem. I'm going to start by dealing with Hooke's law. So Hooke's law, we are saying T, the thrust, equals lambda, and lambda is 19.6, times the extension, where are we? 0.5. And I've got that because we're compressed 0.5, because we started at 1.5 and we've gone down to 1, divided by the natural length, which is 1.5. So that equals 98 over 15 newtons. Finally, let's resolve our forces parallel to the plane. Now I'm going to take down as the positive direction, because I kind of feel like this thing is going to be moving, accelerating down the slope like that. So that's why I'm going to say that's positive. So pulling us down, we've got the thrust, and we've also got the weight. So 0.5 g sine alpha, because it's the parallel component of weight. So that's pulling us down. Pulling us back up, we have got the friction, and that must equal the mass, 0.5, times the acceleration. And the acceleration is ultimately the thing that I'm trying to find. Now, we've got values for each of these things. So the thrust is 98 over 50. 0.5 g times sine of alpha. Well, we can calculate that because we've got sine alpha. So this is 0.5 g times 3/5. And then the friction we've just worked out, 0.08 g. And that equals 0.5 a. Now, if we rearrange this, we get A equals 17.4 meters per second squared. I've rounded that to 3 significant figures. So generally in these questions, we're resolving forces and we're applying Hooke's law, and you might get to a point where you think you can't find any more, in which case if you are doing the resolving forces part, you need to move into the Hooke's law part, and vice versa. If you get to a point in Hooke's law where you can't go any further, you need to start resolving forces. So that's a situation involving dynamics. Now, if we just go back to the specification, so we've kind of looked at this part here, solving some problems involving Hooke's law, and we've dealt with the formula, and we've also thought about a situation, just the previous situation where we had a compressed spring. Next, what I want to look at is the elastic energy, and the elastic energy formula is here. We just want to have a look at where it's coming from and how to then apply it. So for the elastic energy, if we take a graph of the applied force, so the applied force could be the thing that is that is compressing the spring, or it could be the thing that is stretching the spring. And we draw a graph of that against the extension. It should be linear because we're only looking at Hooke's law before the elastic limit. So we get this kind of linear graph. Now, to find the work done, we do the force times the distance, or the force times the displacement. In our graph here, that would be the area under our graph. So the area under our graph we can go and work out because it's just finding the area of a triangle. If our extension is x, the thing has been extended by x, and the applied force obeying Hooke's law is lambda x over L. What we can do is find the area of the triangle here, and that should tell us what the elastic energy is, because we are doing work against that elastic energy. So the area of the triangle is a half times the base, and the base is x, times the height, which is lambda x over L. And I'll just put a 1 under there to make it very obvious. So we're doing 1 times x times lambda times x, so that's lambda x squared. And then on the bottom, I'm doing 2 times 1 times L, so that's 2L. That is your formula for elastic energy. They do not give you that in the formula book. That's just a formula that you also need to learn. That's where it's coming from. Now, this question we did at the beginning. We did part A and we got lambda as 14.4. For part B, this is a really straightforward one. Find the elastic energy stored in the string. We are just having to remember a formula. The elastic energy is lambda, which we've just worked out, 14.4, times x, which we worked out as 0.25. Because if you remember, it was the difference between these two numbers here, squared, divided by 2 times 0.3 natural length. And that gives us 1.5 joules of energy. I would be very surprised if they gave you a question that easy in the exam, but that is a past paper question. I guess they're basically checking that you've learned the formula. More likely would be a slightly more tricky question. So this one here is more tricky. You can see it's split into 2 parts. I imagine the first part is reasonably straightforward. It's only 3 marks. And then we get onto something a little bit harder. Now, like the other questions, if they give you a question with lots of words in it, we really want to turn this into a diagram. So you might want to pause the video and just have a go at drawing the diagram and trying the question yourself. This is the diagram for part A. You can see we've got a natural length of 2, and I suppose the particle is kind of hanging. I haven't put on my forces, but that's what I should be putting on. It's a mass of 3 kilograms, so it's 3g, and there is a tension going up. Now, I'm not going to kind of do this in a long-winded way. I can see, because it's in equilibrium, the tension will be 3g. And I'm then just going to apply Hooke's law. This is really similar to the first question that we did. So 3g, which is the thrust or the tension or whatever we're getting as the force, that's equal to 294x over 2, and that gives us x as 0.2 meters. So that first bit is not particularly tricky, very similar to what we've done. It's the second bit that I was more interested in, because that is looking at using the elastic energy. So we've got this particle. This time it says it's held at a distance of 1.2 meters. So if I had a sort of elastic string and it says its natural length is 2 meters, if I have it kind of shorter than that, it's not a spring, so it's not going to be pushing out like a spring would. Elastic string, it's just going to go limp. So we kind of have this situation, and you can kind of imagine that to a point, before we get to like here, for instance, which would be 2 meters, there isn't really going to be any elasticity in the model until we get beyond 2 meters, where the string will start to have an elastic effect. This could start to get quite confusing, and there are a number of ways of approaching this problem. But one way is just thinking about conservation of energy, and that's the way that I'd recommend you do this. So let's think about different energies, because you're going to get a mark for each. The first thing I want to think about is the loss in potential energy. So that is your mass times your gravity times your height. So I've put the extra formula here for potential energy and kinetic energy. Again, you need to learn those formula. So mass is 3, gravity is 9.8. And really, I'm kind of saying how much height is it losing. So it's falling by 1 meter because it's saying it starts at 1.2 and then it says work out the distance to the equilibrium position, and I've worked out that this is 0.2 meters. So 2 plus 0.2 would be 1.2, so it's an extra meter further, and that's why I'm using 1 as my distance that it's going to travel. So that's 29.4 joules. How's the loss in potential energy? Now, at the start, it doesn't have any kinetic energy because it's held at rest. But we are going to get a gain in kinetic energy. So the gain in kinetic energy, well, that's half mv squared. So a half times 3 times v squared. That's 3 over 2 v squared. We're also going to get a gain in the elastic energy. So gain in elastic energy. And the formula is lambda, so that's 294, times x squared. X is the extension, and the extension we've worked it out over here. So it's 0.2 squared divided by the 2 times the natural length, and the natural length is 2. This gives us a gain in elastic energy of 2.94 joules. So we start with only the potential energy, and then at the end we've lost all the potential energy and we've gained in kinetic energy and elastic energy. So our potential energy equals the kinetic energy gained and the elastic energy gained. So 29.4 equals 3 over 2 v squared plus 2.94. V squared is 17.64. So V is 4.2 meters per second. Now, there will be other ways of approaching that problem, and you can get credited with marks by doing it other ways, but this is just one way that we can approach the problem. So that is kind of a slightly less straightforward elastic energy question, where we're thinking about our conservation of energy. Now, another type of question that I have seen come up is one involving spring. I noticed when I was looking through the past papers, in 2019, you can see at the bottom here, we had a question here with a diagram with a spring, and then I went back 10 years earlier and found a question in 2009. It looks, like a very, very similar diagram. It's a very similar question, actually. I think it's talking about the modulus for part A, the modulus for part A, and then for part B, the speed, and for part B here, the speed. So they're really, really similar questions, and I guess it demonstrates the value of doing lots of past paper questions, because you might find one that's very similar to one that will be in your exam. I don't think this means that every 10 years you're going to get the same question up here. Let's have a go at the 2009 question. I'll stay away from the 2019 question, because you might cover that when you do some past papers. So the 2009 question looks like this, and I thought it was nice because we have it acting horizontally. So we've got this diagram showing a spring. The natural length is 0.25 meters, and so I just want to think about, is it being compressed or is it being stretched? Well, it does say here it's being compressed, 0.2 meters. Now, it is in a smooth horizontal tube, so already I'm thinking I don't need to worry about friction. One end is fixed and one end is attached to a small ball bearing, and it tells us the mass. Find the modulus of the elasticity. So part A, our natural length is 0.25. The extension, in this case, it's not really an extension, it's a compression. 0.25 minus 0.2, so it's 0.05. And then we're going to apply Hooke's law and see what happens. So Hooke's law, somewhere up here, it says we're being held in equilibrium by this force of 80 newtons. So 80 equals lambda times 0.05, all divided by the natural length of 0.25. So 80 equals 0.2 lambda, and lambda then equals 400 newtons. That's a fairly straightforward one. B, the elastic energy at the start. Let's have a read of this. The ball bearing is released by removing the force. Find by using energy considerations the speed of the ball. So we aren't going to have to worry about potential energy because this thing is not being held under gravity. We don't have to worry about any friction, although in real life there would be friction. So really we're thinking it's got elastic energy at the start, which we do want to work out. It will not have any kinetic energy at the start because it's not moving. So our elastic energy at the start, using our elastic energy equation, is lambda, which is 400, times x squared, so 0.05 squared, all divided by the 2 times the natural length, and the natural length is 0.25. So that gives us 2 joules. Then we are thinking, it says, use energy considerations, the speed of the ball, just as the spring attains its natural length. When it's at its natural length, it will no longer have elastic energy. It will all be into kinetic energy. So we want the kinetic energy at the end. And that is half mv squared. So half times 0.36 times v squared. So that's 0.18 v squared. Now, because it's all being converted to kinetic energy, we can write that 0.18 v squared equals 2. So v, if we rearrange this, is 3.33 meters per second. Oh, that's the wrong unit, isn't it? Let's rub that out. Should be a 1. To 3 significant figures. So that's a question involving elastic energy horizontally. Now, to finish, there's a more difficult question to have a look at. One where we combine topics. I'm going to be quite quick going through this. Now, I might skip part A, which is 6 marks. To carry out part A, you need to go back and have a look through your circular motion work. But if you remember, in circular motion, we need to be thinking about resolving forces vertically. When we have a situation with vertical motion acting in the horizontal plane, we want to resolve forces this way, so that would be 2g. And we also want to resolve forces going into the center. And here you've got like the tension pulling us up. Here we've also got kind of the horizontal and the vertical components of the tension. I think I will probably just skip through these parts because I'm not going to have time to do them all. For part B, I think I will go to B part 3, calculate the value of lambda. Actually, no, we need to do part 2 first. So in part 2, I think in part 1, part A, we end up, once we've resolved our forces going into the centre, we end up with T equals 2L omega squared. And then I think we use that to find L. So we get a natural length of 10/3. And then it says to find lambda. So to find lambda, we need to find what x is. X is the extension. Now, in this question, it's a little bit confusing because they're using L, and usually L is the natural length of the string. But here, it says the natural length is 3. L is the stretched length, and that is where they've made it a little bit confusing. So X is this stretched length, which is 10/3, minus the natural length, which is 3. So our X, the sort of extension, is 1/3. Then we just apply Hooke's law to the situation. So in part 3, Hooke's law, we take whatever they tell us the tension is. Well, in this question, they've actually been quite kind because they've told us the tension, 20G, and that equals lambda times 1/3 divided by the natural length, which is 3. This gives us lambda as 1,764 newtons. Okay, so a little trick there where they're kind of using L in a different way. For part 4, find the elastic energy in the spring. We're literally just applying the formula that we should have learnt. So it's lambda 1,764 times x squared, so 1/3 squared, all divided by 2 times the natural length of 3. So 32.67 joules. If you do go ahead and try this question yourself, cos theta is 0.1. So you might want to just go back, have a go at part A, which is a show that, and then have a go at part B, 1 and 2. Now, I rushed a little bit at the end because I was running out of time, but I think I've managed to get through everything I wanted to. So we've had a look over Hooke's law, and the main thing that you need to remember is that the formula is not given. Usually you're resolving forces vertically, horizontally, maybe perpendicular to a plane, parallel to a plane, and you're also applying Hooke's law, and then you end up with some unknowns that hopefully you can solve. You might also get a question involving elastic energy, but usually it's tied in with elastic energy, potential energy, and kinetic energy, and very often it's thinking about the conservation of energy in a question. Now, if you found that useful, there are other sessions available, and you can go and have a look at those on the e-sgol website, and there are previous sessions from previous years. I'll finish there. Thank you.